Okay, time to get started. Let's get going. Now, real quick, for those of you who just walked in, don't forget to do the attendance quiz. Again, the attendance quiz disappears deliberately 2 minutes after class starts. That's to promote punctuality. Anyway, make sure you get that done. You got about a minute left until it disappears. So Canvas, look at the quiz for today's date. This is the answer. Make sure you hit submit or whatever it is. Make sure you confirm you got the point. Right? That's what matters. Okay. All right. So back into the math. We're going to proceed. Let's rewind real quick. Come back and note that this is the big result that we're going to be making use of. And that is when an equation has x's and y's in them, but only, very importantly, only as part of that expression, square root of x squared plus y squared. The equation has x's and y's only in that form. Then you get this really nice geometric conclusion of, hey, it's rotationally symmetric around the z-axis. Fabulous conclusion with, casual glance needed to check that you can do it. So we talked through last time why that's true, a couple different points of view, and we did this example last time. I'm going to do another one here. Here's an equation. Now let's ask, does x and y appear not only in the special form, but only in the special form? Cannot emphasize that enough. And right? So because x and y are only in the special form, this thing's rotationally symmetric around the z-axis. Huge conclusion. And related huge conclusion, because it's got that rotational symmetry around the z-axis, oh, come on, I can do better than that. Around the z-axis, I can pick any plane I like that contains the z-axis. Doesn't matter. Whatever. Right? I mean, I encourage picking a coordinate plane because it's a lot easier to write down the equation, right? But you can technically pick any plane you like. All right, and if I can figure out what the cross section is in that plane, then I just say, look, it's rotationally symmetric, so I'll just rotate that around the z-axis and victory. So, okay, what does this cross section look like? So we plug that in to our equation, and we see what comes out, and what comes out is this right here. Now, y'all, again, have to flash back to high school algebra. I don't know at what stage of high school algebra they do that these days, but hopefully you'll recognize this as being a hyperbola, and specifically a hyperbola oriented like this. Now, if you're anything like I was, when I was y'all's age-ish, high school, whatever, I used to find it a little confusing. Wait a minute, how do you know if the hyperbola goes that way or this way? How do you remember it? Some people like to memorize little rules about where is the minus sign. I think that's a mistake because then you have to remember, wait a second, is the one on the which side or the other side? And it's real easy to get that backwards. Think about it from an algebraic point of view, a geometric point of view. If you're not sure how to be confident with that, come talk to me in office hours. I'll be very happy to show you my little hack. But anyway, make sure you can get that straight. Punchline being, now I know the cross section, and I can then just take that cross section and rotate it around the z-axis. I get something that looks like that. So that's what this surface looks like. It's called a hyperboloid. We're about to see momentarily that there are different kinds of hyperboloids. This one, as it turns out, has sort of a single connected component, so we call it a hyperboloid of one sheet. Okay. All right. Yes?
Wait, so the reason it's rotational, it has rotational symmetry around the z-axis
is because, so it's got rotational symmetry around the z-axis because x and y appear only in that special form.
Okay.
Yep, exactly. Okay, let's see another example. Actually, this next one's kind of a twist. We've only been talking about around the z-axis. That's just to get the ball rolling. But I want to point out, if you come back and look at this first argument, not the cylindrical argument, but this initial argument that we made, there's nothing particularly special about the fact that we chose X and Y to be in the special form and Z to be the resulting axis of symmetry. We're just looking at distance from one axis based on something we know about the variables corresponding to the other axes. And so you can make analogous arguments around the x-axis and the y-axis. And that's a fantastic little exercise. I want to encourage y'all to think that through. Don't just kind of do a little mental find and replace, right? Think through the argument, draw the picture, think through what does the special form represent in terms of a distance, and really think through why the argument should work, right? All the little details. The punchlines are, conveniently, exactly what you would expect. So let's use one of those new results. Think about this example. So what is that? Now, do X and Y appear only in the special form? And sadly, no. There's a minus sign there. And there's not a minus sign there. Right? So there's no sort of fancy algebraic rewrite cleverness that I can do to put this into an equivalent form that has the required property. So this thing here, it just isn't rotationally symmetric around the z-axis. So we lose on this one. And side note, most surfaces aren't rotationally symmetric around the z-axis. But with a little bit of a clever rewrite, you see what I did here? While X and Y don't appear in the special form, Y and Z do. And again, not only do they appear in the special form, they appear only in the special form. So this is rotationally symmetric around the x-axis. And so there's my axis of symmetry because of, and here let me highlight a little bit better because of that. Everybody on board? All right, so again, pick your favorite plane. Go crazy. Doesn't matter. I like to keep my life simple, so I'm going to pick arbitrarily this plane, but I could have picked the XZ plane, and if I really wanted to just pointlessly make my life difficult, I could have picked the plane y plus z equals 0. Right? That would work too. It just wouldn't work anywhere near as conveniently, and why would we ever want to do such a thing? So I encourage you not to play that game. But anyway, in this plane, the XY plane, we have z equals 0, which I can plug into there, which makes that turn into this, which again we recognize, again a hyperbola, again flashbacks to high school. Make sure you can get it straight as to which way it goes. It's easy to mess that up. Make sure you have a reliable understanding there of that old algebra. And here's what that cross-section looks like. And so again, it's all over but the shouting. It's rotationally symmetric, and I have a cross-section. So just take that and rotate it around the x-axis. And it's really hard to draw. Three-dimensional drawing's hard, right? By the way, I'm gonna make the following pitch many times throughout this semester. There are things to know about three-dimensional drawing, and it takes practice to be good at three-dimensional drawing, right? So learn the tricks and clock the hours, right? And you can get reasonably good at three-dimensional drawing. It is an extremely valuable tool in a class like this. This class is unavoidably geometric. There's no way around it. You cannot algebra your way around needing to understand the geometry of it. So think of it as, don't think of geometry as a tool for getting what you really want, which is answers. That's not true. Geometry is the goal. It's to understand the geometry and also to use the geometry. So again, being able to draw reasonably decently doesn't have to be beautiful. I would put this up as a pretty good example of a not very beautiful picture. And I'm sorry, I did my best. I don't know how to do much better than that. So think of something like this as your goal, is to be able to produce a drawing that is, well, I guess I can kind of see what's going on there. Okay. By the way, everything I know about mathematical drawing, in particular aimed at a course like this one, is in my playlist called Miscellaneous Topics. And there's 2 recordings. One's called Drawing 1 and Drawing 2. And it's basically every tip and trick that I know about three-dimensional drawing, and then several examples where I go through in detail all of the considerations that informed every pen stroke that I did in producing the drawings that I ended up producing. So hope you might find that useful. Okay, anyways, the point is you rotate it around and you get whatever that is. So notice, again, it's a rotation of a hyperboloid. Rotation of a hyperbola, so we call it a hyperboloid. Notice, though, it's got kind of 2 connected components. It's sort of, we're rotating sort of morally a different way, and so we get a different thing. And 2 connected components, we call it hyperboloid of 2 sheets. Okay. So, by the way, the reason I spend a lot of time on this business about rotations is that I think it's a powerful tool. It's a way to turn a 3-dimensional problem into a 2-dimensional problem. And it comes up surprisingly often. So I think the book undersells this tool, and I want to spend a corresponding amount of time in class. Okay. Here's a nice natural question to think about. I got an equation here. Convenient equation. I know what this looks like. Distance from the origin is 13. So this is a sphere. Okay, here's a weird hypothetical. But let's just play the game. Hypothetically, if everywhere I see a z in this equation, I were to replace it with 2z, what would be the effect on the geometry? So again, but I always like to think in terms of the relationships between algebra and geometry. So here I'm talking about a kind of something that I would do to the algebra, and the question is to figure out what does that do to the corresponding geometry. All right. So what's the set of solutions to this equation? Everybody see what we're interested in asking? Okay. By the way, to emphasize, my question is not what does this look like? My question is what is the effect of making this change? Right? You can determine what this looks like by making a rotation argument, right? I see the x squared plus y squared, proper form, blah, blah, rotationally symmetric, dimension reduction. So you could do this without the following argument. But the goal here is to understand the effect of that little algebraic tweak. Okay, well, so the big idea here is that a point like this that works in that equation obviously won't work in the new equation. But correspondingly, a point like this will then work in the new equation. Does that make sense? How are we doing? I mean, it's an innocent observation, right? I mean, I had a z, that 12 was plugging in for where the z is. If I plug in 12 for where this z is, then it crashes and burns. Obviously not going to work. But if I put a 6, right, then the 6 times the 2 is the 12 that made it work before, and then everything follows. It's a smart alecky sort of, snap back to the change that we made algebraically. So the punchline is the solutions here and the solutions here, there's kind of a one-to-one correspondence. You give me a point like this, I'm going to come back with a point like this. And notice that all that has happened is that the z-coordinate has been divided by 2, and I claim then that means that the surface has been squished in the x direction. So that is the effect. When you do an algebraic tweak like this, the effect is that you squish in the z direction by a factor of 2. Everybody buy it? Okay. All right, so let me get rid of everything else here. So this algebraic tweak causes this geometric result. Let me phrase this a little bit more broadly. we're going to be tempted to say we multiplied by 2 here. Right? I guess you could say that we're multiplying the z variable by 2. The z coordinates then get divided by 2. So in some reasonable sense, the effect on the geometry is kind of the opposite of what you did in the equation. Does everybody see that? This is a shockingly consistent sort of summary. Lots and lots of examples. So you could do this, make the same argument by and end up with a squish in the x direction. You could insert a minus sign instead of a factor. That will reflect in the appropriate direction. You could translate. You could replace z with z plus 5. The result will be to subtract 5 from the z coordinates of all the solutions. Right? In other words, a downward shift. So it's a shockingly consistent little pattern. And I think I have that. Yeah, here we go. Right? So whatever you do to a variable in an equation, that's sort of the opposite in some reasonable sense. The opposite happens to the surface. Okay. So again, lots of examples. I'm going to go through these pretty quickly. They're pretty straight reads. But notice what I did here is I replaced every x with x over a. The opposite of dividing by a is multiplying by a. And so we would expect that this would stretch in the x direction by a factor of a. Everybody happy? And then likewise, with the y is getting divided, if you will, by b, and so we expect a stretch in the y direction by a factor of b. Likewise, z. Here's a little subtlety. A lot of students will get this wrong in these examples, which, by the way, we already know what that surface is. We already know what that surface is, right? Rotational symmetry arguments. But in this first example, what am I doing to x? And let me first show you the wrong answer. This is the landmine that a lot of students step on. A lot of students think that I divided x by a squared. That's wrong. That's not what happened. I did not replace x with x divided by a squared. Because in the original equation, x is getting squared. This a squared that I've got in the denominator is not getting squared, right? So, in fact, if I wanted to think of this as a replacement, I'd really have to rewrite this term. Let's see here. Let me just kind of scratch and sort of put it over here as x over a squared. And now, perfectly appropriate, x, the thing that is getting squared there, x is being replaced by, you see, x over a, and you see that whole x over a replacing what had been just x is getting squared. So the stretching factor here is not a squared. The stretching factor here is just a. Real easy to mess that up. Right, so now I show you where the landmine is, right? You make sure not to step on it, right? Be careful about this little subtlety and don't expect that equations will always come to you in a form where it's sort of written in the way that's most convenient, because that's not how life works, right? Tragically. And sometimes you have to sort of tweak it appropriately. Okay. So there's some other examples in the book. You can take a look at those. I encourage you to think it through. But we're going to move along. By the way, we're now done with section 2.1. Moving along to 2.3. Oh, hey, what happened to 2.2? You may wonder. So 2.2 is about limits. And it's beautiful mathematics. It's important mathematics. It's historically critical mathematics. There's cool stories historically about the stuff that's in 2.2, right? And if this were Math 531, I'd be all over it, right? If this were Math 222, I'd be all over it. But this class 219 is our focus is geometric intuition, problem solving, right? Rubber meets the road. Y'all are mostly engineers, and as much as I would love to talk about pure math and rigor and proofs and stuff like that. It's just not what this class is about. So we're just going to skip 2.2, and I'll wave my hands in a couple of moments down the road and talk about what ultimately doesn't matter. Okay, so we're going to start talking about derivatives. Derivatives are a big deal. First unexpected fact, while in single variable calculus, there's only the derivative, right? There's only one. It's taking a derivative. There is only one taking a derivative, right? Not so with multivariable. There's various different kinds of derivatives. So we're going to talk through all of them, pretty much. But before we do, I want to address, why do we use, if they're different, why do we use the same term derivative to describe different things? And that's a reasonable question, right? If things are different, you should use different words. So why are we using the same word? And it's because they all have something in common, right? They all have this unifying feature. And so this, going through the course, I want you to take this really seriously. This is how you should think about derivatives. Now, I know you have pre-existing points of view on derivatives, slope of a tangent line, stuff like that. Right? That's okay, fine. And those will come up here and there among the many different kinds of derivatives we'll be talking about. But what I would like to be the cornerstone of your point of view of how do I think about derivatives, it's this right here. In their different ways, they are all relationships between input changes and output changes. In their different ways. All right, so be on the lookout for this unifying feature as we go through and talk about these different kinds of derivatives. Now, I'm going to start, as the book does, as most books do, with partial derivatives. And there's some, non-silly reasons I want to start with partial derivatives. There's also a very strong counter-argument. In fact, if it were up to me, we would not start with partial derivatives, but since our book does, I feel like that tips things the other direction. But there is a better way to think about derivatives, and this isn't it. Partial derivatives are kind of nice in certain ways, but ultimately they're misleading about how you really ought to think about derivatives. There is a best way to think about derivatives, and it is not partial derivatives. Now, so what is the best way? We'll get there. Take us a couple days. Be patient. But anyway, full warning. Please don't establish this. Please don't cement this idea that we're about to talk about as here's how I'm going to think about derivatives and everything else is a tweak on that. Not so. This is a ultimately vaguely misleading way to think about derivatives. Okay, that said, it is useful, so we do have to do it. Here we go. Here's the big idea. It's ultimately not that much to a partial derivative. We don't really know what to do with taking the derivative of a multivariable function. We know how to take single variable derivatives. If we only had one variable, we'd be in business, but we have several variables. So here's the ultimately kind of unsophisticated, kind of naive idea. Let's pretend we only have one variable. Right, we have several variables, but we're just going to go ahead and assume and treat all the variables as being constants. We're going to stick our head in the sand. Right? Pretend we're going to play make-believe that these variables aren't variables, except for one that we're going to treat as a variable. And now, in fact, what is left over is a single variable function. Right? If you fix all of the variables except for one, then if they're fixed, they're not really variables anymore, and so we really only have one variable. And then just play the usual game. Take the usual derivative. So that's what a partial derivative is. Again, I hope you're suspicious this sounds vaguely unfair, right? Am I allowed to do that? Can I just ignore other variables? And you should kind of have a problem with this. Right? Let me also point out, just I want to nurture the suspicions that you should have in your mind right now. What reason do we have to believe that this little game of make-believe is going to produce a useful construction? Right? I mean, you can define anything you want. Doesn't mean it's useful or relevant to anything meaningful. Right? How do we know this is meaningful? To be determined. Right? So again, you should be suspicious about that for the moment as well. All right? That said, so I while I will show you those uses and sort of the naturality of this, I want to sort of put that off for a minute. So here's some notations that we use. They're all kind of believable. I will point out that this one's a little bit weird, where you put the variable that you're going to continue to treat as a variable as a subscript. A little bit of a weird notation, but not that different from the old Newtonian notation for derivative, f prime, right? But I'm not writing this as a fraction, right? So in that sense, it's like Newton's notation, kind of, sort of. And this has its moments. It's useful sometimes. Okay. Let me also call your attention to this symbol right there, the partial derivative symbol. And a lot of students get a little bit lazy on this and will write it as being a D. It is not a D. You cannot write it as a D. That would mean something else. That is not okay. Make sure you don't write these as Ds. Cannot emphasize that enough. It's not optional. If you write it as a D, it's wrong. Right, so make sure we're clear about that. It's also commonly misunderstood as being a lowercase Greek letter delta. Nope, it's not that either. Right, this is a new little symbol that I think may have just been created for the purpose of talking about partial derivatives. Anyway, if you're not accustomed to making that little symbol, you might have to do like I did when I was your age and actually pull out a sheet of paper and go through the tedious, silly seeming process of practicing how are you going to make this little symbol and get to where you're comfortable with it. Okay, so let's do some. Let's see how we compute these things. Now again, you should still be suspicious. Why would this be useful for anything? Why are we this? How do we know this isn't useless garbage? Right? You should be worried about that still. But anyway, let's go ahead and compute some. I'm going to take the partial derivative here of we got this big function, scary. Oh gosh. Okay, it's a product of three factors. One of them is a composition with a product. Oh gosh, cotangent. Oh man, I hate cotangents. I never can remember where the minus sign is. Stuff like that. So this is worrisome. We're going to take the partial derivative with respect to y. Let me show you how easy it is to compute partial derivatives. It's super easy. The big point is to remember that whichever one you're taking the partial with respect to, you treat as a variable, and all of the other variables, you treat them as a constant. They act like constants because that's what we're doing with partial derivatives. Meaningless or not, to be determined, but that's how we compute partial derivatives. So, x and z then are constants. That means that x right there is a constant. That means e to the x is a constant. That x is a constant. That z is a constant. That means this thing on the inside here is a constant. That means this whole cotangent thing is a great big ugly nasty constant. And the only thing it's not a constant is the y squared, right? And taking the derivative of y squared is easy. So the y derivative of y squared is 2y. Constants do what constants do, which is just stick around. Boom. No product rule. No chain rule. Everybody on board? Isn't that nice? This is super easy. So I like to nominate, by the way, I think partial derivatives are the easiest derivatives to compute. I think they are easier than single variable derivatives. Because if this was a single variable derivative, I don't get to just go around treating large fractions of my expression as constants, right? If this were a single variable, analogous single variable function, I'd have to be using the product rule and the chain rule and all that stuff. And here, constant. Everybody on board? All right, couple other examples. Again, let's be quick about this, but it's worth saying. So we're going to take an x partial. We're going to take a partial with respect to x. Cool, that means y is a constant. That means y squared is a constant. That means I have a function to the power of a constant. At a casual glance, you look and you see a function to the power of a function. Yikes. Logarithmic differentiation. Do y'all remember logarithmic differentiation? If not, it's a cool technique. It's not critical that you know it, but kind of inconvenient. But no such problem here. Function to the power of a constant. And it seems a little weird to do this move, the power rule. Doesn't seem like you're supposed to be able to do that, but it's a constant, and so yes, you can. Don't forget the chain rule, of course. Everybody happy? Likewise, let's take a partial of this expression with respect to z. Oh, yeah, that means x and y are constants. So this is not a function to the power of a function either. This is a constant to the power of the variable. This is just an exponential. This might as well be k to the power of z. And so exponential rule, don't forget the chain rule, etc. All right. Okay, whoopsie. That's the wrong, this thing slides around. Okay. So now let's address the elephant in the room. But how do I know this isn't meaningless garbage? Always a legitimate concern. Right? Again, you can write down any definition you want. It's a free country. But if you write down a definition, you've got to demonstrate that it makes sense in some way. It's got to have some connection to something. It's got to look like something or relate to something, right? It can't just be nonsense. So there is a really nice interpretation here. Actually, there's several nice interpretations. Let me flash you back to last time we were talking about how different sorts of pictures you can draw have different sorts of calculus. Right? So I'm going to start off telling you about what I'll call the calculus of graphs. Notice we're looking at a graph here. So this curve here is a graph of some function of two variables. What I'm about to show you only applies to graphs. What I'm about to show you has absolutely no bearing on how to interpret partials if you're looking at level sets. And it has absolutely no bearing on how to interpret partials if you're looking at some other construction, right? So I cannot emphasize this enough. This is graphs only. Okay, so that said, let's suppose we are at the point A, B in the domain, and let's suppose that I say I want to take the partial derivative with respect to y. Okay, let's do this. And good news, if you look at our definition here of a partial derivative, two-step process. First, hold the other variables constant. Second, take the usual derivative. And I claim we know exactly what both of those steps look like. So in this example here, I know how to interpret geometrically both of these sort of two steps that define this partial derivative. So let's do it. First of all, there's only one other variable. Let me get my colors straight here. So, we're using blue for y. So, y is our only variable. That means x is to be treated as a constant. Don't forget, we're at this point where x is already a. So if I say I'm going to treat x as a constant and it's starting off as a, that means it stays as a. And so that means that I'm confined to this plane, x equals a. Is that cool? Geometrically, let me say that a little bit differently. I've got this graph that I was looking at, but I'm only interested now what's happening in this vertical plane. Said differently, I'm going to take a cross-section of my graph through this plane, x equals a. I'm going to take a cross-section, you might say perpendicular to the x-axis. Or you might say, I'm going to take a cross-section, a vertical cross-section parallel to the y-axis. Does that make sense? You got to make sure to. It's really easy to kind of get the geometry. I mean, it is perpendicular to the x-axis. It is parallel to the y-axis. It does have an interesting geometric relationship with both of the domain axes. You got to make sure you're straight on which one is which one. Okay. All right, so I'm going to be looking, instead of the whole graph, I'm now going to be looking just at that cross-section. Now let's talk about that cross-section for a second. What's going on with that cross-section? And I will point out that it's giving us, let's see here, it's giving us values of the function interpreted as heights as they depend on y. In other words, as I move in the y direction. All right, my input variable is the horizontal direction. My outputs are being vertical. This is a graph of my new single variable function. This cross section is literally the graph of the resulting single variable function. And so with that in mind, when I come down here and say, well, how do I take a derivative with respect to y? Whoops, wrong. How do I take a derivative with respect to y? We're already armed on that. Derivatives, if you're looking at a graph of a single variable function, which we are, the derivative with respect to y is just, it's just the slope of that tangent line. Old news, Calc 1. So there's your punchline. This is the interpretation. A partial derivative with respect to y is the slope of the tangent line. Kind of like in single variable calculus. And the only little asterisk is that you have to, we do have to be clear that we're talking about a graph. I cannot undersell this point, right? Partial derivatives are not just the slope of the tangent line of whatever picture you might be happening to look at the moment. Absolutely not. Graphs only. And the reason they don't make a big deal out of this in single variable calculus is, again, every picture they draw is a graph, so they don't need to clarify. So slope of the tangent line to the graph, and then you also need to specify. They don't specify in single variable because there's only one direction to go. Here we have to specify in the y direction. You're moving literally in the y direction, not just whatever random direction. Okay, so I'm going to leave it as an exercise. It's an argument that you can produce by shamelessly copycatting what we just did. I mean, literally just like cheat off of the work that we just did there, right? Think about what an x partial should look like, and what you're going to find is it's the slope of the tangent line of the graph in the x direction. It's exactly what you would expect. But again, healthy exercise to go think through those details. Is everybody on board? Okay, so our worry, I hope, is gone. Right? I was trying to encourage y'all to be worried about, is this meaningless nonsense? This seems a little too easy, a little too good to be true. We just made up something because it's convenient. I hope it's useful. It is useful. Check it out. Geometrically natural. That means something I can see, right? Very familiar even. Lovely. Okay, so we have a useful construction. Okay, now again, that was graphs only. Let's think about some of our other types of pictures. y'all recall I like this literal picture, like so, where you literally just draw the domain, and then you literally just draw the target, and then you literally represent the action of the function as moving points from the domain to the target, like so. How would I interpret partial derivatives in this context? Again, let's just think it through. If I'm going to take a partial derivative with respect to y, what that means is the other variables are going to remain constant. That means that wherever you might happen to be, the x-coordinate and the z-coordinate are not allowed to change. That means they have to stay whatever they had been. That means you're stuck on this line. That's the line where x is always a and z is always c. You're not allowed to move off of that line. All right? What's an interpretation of derivative that I can make sense out of here? Can I talk about slopes? Absolutely not. This is not a graph. Couldn't possibly even draw a graph of this function. The graph of this function would be a picture in 4 dimensions. It's got nothing to do with this at all. Slope will not have anything to do with how we interpret this right here. Is that clear? Again, I make a big deal out of this because so many students don't. Let me say it this way. The less of a big deal I make out of this point, the more students will step on this landmine and make inappropriate interpretations, and there are bridges about that. Okay, so I'm going to make a different interpretation. And again, I know y'all have several different takes on single variable derivatives, and that's super. One of them is that it is what you multiply by an input change. Right? If I'm stuck on this line, I can talk about moving by some distance in the y direction. We'll call that dy. And of course, when you do that, that'll produce some corresponding output change, which we'll represent as df. Linear approximations and all that. And what's the relationship between input changes and output changes? And again, that flashbacks to what I just said at the start of this section, but hopefully also flashbacks to what you remember from single variable calculus. A derivative is what you multiply by input changes to get output changes. Does that ring a bell? Everybody remembers that one? So that'd be my take here, right? If you want to know on this literal picture, how do I think about a partial derivative? Well, it's the factor that relates that to this. It's what you multiply that by to get this. So in this case, I would interpret, that looks like about 0.6, maybe, something like that, a little over a half, maybe. 0.6, 0.7, right? So that's what the partial derivative looks like here. Everybody see the difference? It's not a slope. Yeah? Okay. What if you're looking at level sets? Again, not a graph. This is a really common landmine for students to step on. We got some function, and here's the picture we're looking at, and partial of f with respect to x. And a lot of students will think, oh, okay, well then it must be the slope of this tangent line. It must be that slope right there, and that is nonsense, because that's not a graph. Okay, so how do we make sense out of that? Now, I will remind you, my favorite way to think about my favorite way to think about level sets is to think about, hiking, right? When you're hiking, the mountain that you're actually hiking on, the value of the function is height. Nice little twist, if you really think about it. The mountain itself is the graph of the altitude function. If you think about it, what is the graph? The graph says take whatever your function is and make that your height, which is what altitude is, right? So, lovely little fact. Mountains are, surfaces of mountains are graphs of their own altitude function. So I like to think of a situation like this as the function is an altitude, and this is just a way for me to keep track of what it looks like as I'm hiking around on that mountain, right? And so, in other words, slope of the graph. So, all right, well, if I were hiking in the x direction, right, if I was going this way, I'm going to appeal to your geometric intuition. Look how fast I'm cutting through these contour lines, right? I'm gaining 100 feet over very short distances. That looks really steep to me. Really steep graph means a large value of the partial derivative. So in the x direction, I would say that looks kind of large. How large? Well, that's one of the unfortunate things about level sets. I would have to indicate some scale. I would need a horizontal scale by indicating the 1, 2, 3, 4, 5 on the x-axis and the y-axis, and then I would need some sort of scale. I would need to indicate specifically the altitudes at these various. Okay, so there'd be a little. Yeah, so I can't tell you exactly how large based on this picture, but it looks steep. On the other hand, if I were moving in the y direction, now I'm still thinking about a y partial. I'm still cutting through contour lines, but look how much more horizontal distance I get every time I make it to the next contour line. I did that over a greater horizontal distance that seems less steep, and therefore I would expect the y partial to be smaller. Does that make sense? So I can't point exactly on this picture to that's what the partial derivative looks like on this picture, but I can get some sort of relative sense that I feel like the x partial is greater and I feel like the y partial is less. Happy? All right. Okay, moving along. So linear approximations, y'all probably remember this from Calc 1. I hope you remember this from Calc 1. If not, you'd want to make sure to go and review. But certainly I would expect you probably remember this formula. Let's talk about what that formula is. And there's different ways to say this. I like to think of the linear approximation as the unique degree 1 polynomial. So I'm going to try to understand my original function f with a degree 1 polynomial, and specifically I'm looking for the one that has the same value and the same derivative as my function f at the given point a where I want to do the approximation. And so what is this mysterious unique degree 1 polynomial that has that property? Here it is. That's called the linear approximation. Let me color code better. There we go. Okay, so again, different takes. You can also think of this as, this is the function whose graph is a tangent line, or you can. I'm sure there's other reasonable ways to think about it, but this is the take I want to use here. Does that all look familiar? Well, we can ask the same question in a multivariable context. I can ask, what is the unique degree 1 polynomial that has the same value as f and all of the same first derivatives, namely all the same partial derivatives as f at whatever point a I might happen to be looking at. So it's just a multivariable equivalent set of requirements. I mean, I can't talk about the derivative because there are several different partial derivatives. And let's face it, if I want to be approximating the function, it needs to be a good approximation whichever direction I'm going in the domain. So, I mean, doesn't it seem reasonable that I'd want to require all those partials to be equal? And good news, here's a formula that does it. That's function right there. And you can check that actually works. Now let me point to one thing that throws a lot of students on trying to confirm that this function does what I claim that it does, and that is it's easy to forget what's a constant. really easy to forget. So in this function up here, when you're taking the derivative, let me do it like this. There's L. When you're taking a derivative, right? You're taking a derivative with respect to x. Okay, so there's your x. This is a constant. This is a constant. And don't forget a, of course, is also a constant. Right? As you're taking the derivative of this L up here, most of what you see there is constants, and you treat them as such. Well, likewise down here, if you want to talk about the derivative of this function L, right? Specifically, derivative with respect to x1, then x1 is your variable, and that's a constant, and that derivative is a constant. That's the one that confuses a lot of people. That partial derivative is a constant. A1 is a constant. That derivative is a constant. This A is a constant. This value of x is a constant. Practically everything in sight is a constant, right? And so as you compute the partial of L with respect to x1, most of it disappears instantly in a puff of smoke, and not hard to confirm that the answer is, in fact, just that constant. Everybody see how that works? Okay, so think through the rest of the details, and this is a pretty good place to draw the line. Y'all have a great weekend. See you on Monday. Yeah. Quick question. Yeah.